Good day, and you're all very welcome to today's CNPS technical session. Ian Cowan, and today is the 16th of August. We're very happy today to have Alasdair Beal back to talk to us. He gave us a talk last year, actually, on some basically doing with regard to the 1905 Einstein paper, which resulted in special relativity, and he had found some fundamental mathematical errors and illogicalities in the paper, which he went in great detail. And of course, the recording is available. But what he's done in the meantime is he's actually had a paper accepted for publication in Physics Essays 38 to 2025. Actually, it's been published now and it's available. So you want to have a look at it if you haven't already for today's talk. Now, so I'll invite Alasdair to come to relativity and time dilation. I think there's a concentration on time dilation, which he wishes to make today, and what he calls Einstein's calculation errors. And the information is that the speaker has in the past identified serious errors in Einstein 5 calculus, which he's just recently published in Physics Essays. Now he'll be discussing these details and their consequences for Einstein's theory. Well, because you've delineated some, so what, but he'll be looking at the consequences for that. Often it might be just here. I can deal with it if it's only me, but if anybody else is having problems, we can we with that. So as I'll be bringing Alan, just for my, we'll give him roughly an hour to speak. If he wants to speak for less than that, that's fine. If he wants to speak for 15 minutes more or 20, there's no problem. It's on guideline, and we'll look. We'll be posting questions, and actually, we find from experience that most of the postings are merely chats between participants, which is fine. Through that source, do say, "Here's a question for Alasdair," or a question for Ian CNPS, and we'll do that, and then we'll bring in people in the green room. We have a number of people in the green, so we put a frank discussion, as they say. So there's Alasdair. I can say good afternoon to you because you're in the same time zone as me. You're very welcome, Alasdair. Welcome back.
Thanks.
And, what I'm going to do now, introductory remarks, is I shall give you the floor and say something about yourself, because people might not have met you before when you presented to us last. And then we have done a little rehearsal, ladies and gentlemen, with regard to Alasdair's slides up and so on. So all you have to do, I think, is just tell me, yes, please put them up now, and I'll do that. Okay.
Okay. Hello, everybody. Today's talk follows to some extent from the talk that I gave last year. Last year's one was about Einstein's derivation of transformation equations, which match the Lorentz equations from his theory. And at the time I did it, I thought that was all I had to say or would have to say on the matter. But then sometime last autumn, a little thought came back to me, and I realized I had left a loose end. which was his derivation of the equations for time dilation. And I suppose most of you at some time in life have pulled at what you thought was just a loose end, and sometimes just a little bit came off, and sometimes a lot of stuff unraveled as a result. Well, it's been an exercise rather like that. There's no fancy mathematics. It's first year high school level mathematics. It's really quite simple, my analysis, but if it's right, the conclusions I think are quite significant. So, Ian, do you want to share the screen now, please? Is that screen sharing all right? Will I put it up again on mine, or do you do it all at your end? Tell me when.
I've put your. Yeah, it's up. It's up now. I think there's a bit of delay. My apologies to everybody. I think there are some internet problems at my end, but I'll go now and I'll max.
That's right. So you've got the screen. So that's the title of my talk: Special Relativity and Time Dilation, Einstein's Errors, and that's the reference to where I've had a paper on the subject published in July this year. The analysis I'll present is based strictly on Einstein's 1905 paper. There are two reasons for that. One is, when I come to a tricky problem, I always think it's important to go back to the source. If there's difficulty making sense of it, go back to the source and at least understand where it all started from. And very often, the original source document actually gives a much clearer idea than things that have followed. So that was why in the first instance, I went back to Einstein's 1905 paper. There's another reason, which is, despite the time that's passed, it's still regarded as definitive by quite a lot of people. Here's a quote from Professor Stephen Hawking, no less. Wait a minute, I'll take off the thing that's hiding a bit on the screen. Right, that's it. This is what Stephen Hawking had to say in the preface to a 2008 edition of Einstein's papers. The details of Einstein's reasoning and the simple algebra behind it are explained nowhere better than as found here in Einstein's own words. So there's certainly people that still regard the 1905 paper as valid. Special relativity is famous for having equations that stretch and shrink time and distance for bodies traveling at high speeds. In particular, there's a transformation equation for time and a similar one for distance. And then from that, there's an equation for time dilation, which is the slowing of a clock traveling at high speed. Quite an important point to note is that Einstein was not actually the first to propose these equations. The transformation equation was proposed by Lorentz in 1904, and the time dilation equation was proposed by Larmor in 1897, and its application to moving clocks was proposed by Cowan in 1904. So Einstein wasn't the first to come up with these equations. The novelty of his paper was his claim that these equations could be calculated from special theory of relativity without the existence of an ether. So he didn't present new equations in 1905. What he presented in 1905 was a new explanation for equations which were already known. His special theory of relativity is based on these assumptions. And I've copied these as scans directly out of the published version of his paper, so you can see that I'm not misquoting in any way. The laws by which the states of physical systems undergo change are not affected whether these changes of state be referred to one or the other of two systems of coordinates in uniform translatory motion. And the second principle is any ray of light moves in the quote stationary unquote system of coordinates with velocity c, whether the ray be emitted by a stationary or by a moving body. He then a little later in the paper elaborates that the principle of the constancy of the velocity of light in combination with the principle of relativity also means that light is propagated at velocity c when it's moving in the moving system. So its velocity is c in the stationary system and also in the moving system. And those are the fundamental principles he builds his theory on. He then builds his analysis. He starts with two systems of coordinates. The axis x of them coincides, and their axis y and z are parallel. To one of the systems, that's small k, he says it's traveling at constant velocity v relative to the other stationary system, which is capital K. Then the coordinates in those systems are defined as, in the stationary system, x, y, z, and t for time. And in the moving system, small k, the coordinates are xi, eta, and zeta, and tau. Now, I know generally people don't use, they use dashes and so on, rather than the Greek letters that are shown here. Again, I've stuck exactly to Einstein's notation so that you can see when I quote him that I've quoted him accurately, and you can compare what I say he said with what he said and check that I've not done anything naughty there. So that's the reason for the classical notation. He then moves on he sets up he's famous for his thought experiments, and basically his analysis is based on a thought experiment. He places, these are stationary system coordinates. He says, let's have x dash equals x minus vt. So if a point is at rest in the moving system, it has the value of x dash is independent of time because it's subtracted vt from its x coordinate. I hope you follow that all right. And in the moving system, tau is can then be a function of x dash, y, and z and t, which are stationary system coordinates. This is to set up a basic relationship between the two coordinate systems. The key point is x is the x coordinate of something as measured in the stationary system. X dash is its x coordinate with vt removed. So it is therefore, if it's at rest in the moving system, x dash is independent of time. He then proceeds with his thought experiment. From the origin of the moving system K, a ray of light should be emitted along the x-axis to x dash and then be reflected back to the origin of the coordinates. A little later, he brings in an additional assumption to simplify the analysis. He assumes that when t equals 0, tau equals 0 also at the origin of the moving system. So in essence, he assumes that when the two coordinate systems, when the origins of the coordinate systems coincide, that's at t equals 0 and tau equals 0. And there's a diagram one of the simple problems with Einstein's paper is that there are a lot of words and no pictures. So I've put in a picture to show what his thought experiment was. And so you can see this is the moving system, small k. Both coordinate systems start at the same point. And from the observer at the origin, a light flash is emitted. In the moving system, here's the observer in the coordinate at the origin of the system. The light flash travels a distance c equals c tau. And of course, in the time it's taken to get to its destination, the origin of the system has also moved at velocity v. In the stationary system, the two observers were together at the beginning. The system, capital K, the stationary system observer, he has emitted a light flash as well. His light flash travels at velocity c relative to his coordinate system, and the two arrive together at their destination. The distance that's been covered by the system, the moving system flash, is c times tau, c equals c times tau. Relative to the stationary system, it's traveled distance x dash, which is alongside that, but also there's the distance that the origin of the moving system has traveled relative to the stationary one, which is vt. So the total distance traveled in the stationary system, when measured in the stationary system, x equals vt plus x dash. And as that's a light flash traveling at velocity c in the system, we have x equals ct equals vt plus x dash. After quite a lot of mathematics, he starts with that thought experiment. He then goes through various calculations, and he ends up with transformation equations, which are set out there, which I'll choose my words carefully here, look the same as the Lorentz equations. Formally, as presented on paper, they are identical. And this was the key thing that Einstein was trying to do in the paper, to show that the equations that Lorentz had already derived from ether theory, and people liked those equations, he could derive the same equations from his relativity theory, which didn't assume the existence of an ether. He then went on to calculate time dilation, the slowing of a clock, caused by its motion, as seen by the different observers. And this is the main part of today's paper. This is how he presented it. He had already calculated the transformation equations. He said, if we imagine a clock which is qualified to mark the time t when at rest relative to the stationary system, and time tau when it's at rest relative to the moving system, you assume that it's located at the origin of coordinates of small k. That's the moving coordinate system, and adjusted to mark time tau. What is the rate of this clock when viewed from the stationary system? So the key question he's asking, if there's a moving clock located at the origin of the moving coordinate system, what is the rate of that clock relative to a stationary clock, a clock with the stationary observer? And this is what he calculated. He said, well, he said, we have evidently the origin of the moving coordinate system is traveling at velocity v relative to the stationary system. Therefore, In the stationary system, the coordinates of the origin of the moving system, the coordinate of that is x equals vt. He then said, we have x equals vt, we have the transformation equation on the left side of the page. If we insert x equals vt into the coordinate system, we get an equation for time dilation. Tau equals t root 1 minus v squared over c squared. And he concludes from that a moving clock will run slow by that equation, seconds per second, or approximately half v squared over c squared relative to the stationary clock. That's Einstein's calculation of time dilation, which he then uses as the basis for all his thought experiments with twins paradox, clocks paradox, etc. Set out like that, I have to, when I first looked at it, I thought, that's simple, it's obvious. If the Lorentz equation is right, that time dilation has got to be correct as well. But then the little question comes back. These equations, transformation equations, match the Lorentz equations, but they have been derived from a different theory. They've been derived from Einstein's special theory of relativity. And so the terms in them, t, v, x, and so on, don't necessarily have exactly the same meanings as they would have in Lorentz's theory. And one of the problems with Einstein is he's often a bit careless about defining things precisely. And the question that I started to look at was, in that equation, what is x? It's an x coordinate. The x coordinate of what? It's an x coordinate of something moving in an imaginary stationary coordinate system. Because Einstein didn't give a definition, an explicit definition of what the terms mean, it seemed to me that you have to go back to the calculations he did to generate his transformation equations. In other words, these equations have been developed from earlier equations. You have to look at what did x mean in those earlier equations, because that's what it must also mean in the transformation equations calculated from it. So I look back at, that's the big question, what is x? I look back at the previous pages in his paper, and I've highlighted in yellow the relevant equations he developed, which clearly have bearing on the definition of what x means. So x dash is x minus vt, and if you remember in the thought experiment with the light flash, x was the coordinate of the destination of the light flash. Then in the moving system, we have c equals c tau. There it says it clearly, for a ray of light emitted at time tau equals 0 in the direction of increasing c equals c tau. So that's the relationship between the x coordinate in the moving system versus time. And interesting is the third equation he presented. And again, it's to do with his ray of light. X dash over c minus v equals t. I've therefore taken those three equations, which are at a key in the middle of Einstein's analysis, to see how that works out for the definition, answer to the question, what is x? First thing to notice with just those equations is the first equation, x equals vt. The third one, x dash over c minus v equals t could also be written as x dash equals ct minus vt. So we have, oops, don't want to give that away. Oops. Yes, so we have x dash equals x minus vt. We also have x dash equals ct minus vt. So you can see from that we must have x equals ct. Now go into the analysis a bit further. Consider Einstein's thought experiment with the clock at the origin of the moving system. If the clock's at the origin of the moving system, its c coordinate must be 0 and x dash must be 0. If we put x dash equals 0 into that equation, we get x equals vt, which is the equation Einstein had. So far, so good. However, if we look at the next equation, xi equals c tau, if xi equals 0, then tau must be 0. And if tau is 0, then t is 0. If we come to the third equation, x dash is 0, therefore t must be 0. Come to the fourth equation, and we have an interesting conclusion. We have x equals vt, and we also have x equals ct. How can that be resolved? Oops, what's this doing? Yeah, x equals ct and x equals vt. That can only happen when t is 0. So these four equations are leading us to the conclusion t equals 0. What's going on? Well, if you have to go back to the diagram of the thought experiment, you can start to work out what's gone wrong. Because a conclusion that tau equals 0 and t equals 0 doesn't take you very far in answering the question, how slow does the moving clock go? If both clocks are showing 0, that's a very uninteresting end to an important thought experiment. If we look back at the diagram, if there's a clock at the origin of the moving system, then if a light flash is emitted by the observer there, the light flash travels 0 distance to get to the clock. So if it travels 0 distance, we end up that c equals 0 and x dash equals 0. And the analysis is basically becomes meaningless. In his analysis, as you can see, t is the time when the light flash arrives at the remote clock. X is the coordinate of the remote clock when the light flash arrives there. If the clock is on the x-axis, x and t are not independent variables. They're connected by the relationship x equals ct. And similarly, c equals c tau. So for the experiment that Einstein defined with a clock at the origin of the moving system, his analysis doesn't produce any meaningful conclusion other than when both clocks are at 0, they are both at 0. His analysis does yield meaningful conclusions for all situations where xi and x dash are not equal to 0. In other words, where the initial position of the remote clock is not at the origin of the moving system. If the moving clock is some distance away from the origin of the moving system, then we have xi equals c tau and x equals ct. Now, digressing very slightly, in the paper I presented last year, I was looking at Einstein's calculations to derive the transformation equations. There are a lot of problems there. And I got the strong impression, some of the calculations really didn't make a lot of sense. I got the impression that Einstein knew at the start of his analysis what answer he wanted to get, which was the Lorentz equations. And to some extent, his calculations were assembled to achieve in such a way as to achieve that answer. I'm not the first to have suggested that. This is a very good and authoritative textbook on the special theory of relativity by Arthur Miller. And I thought this passage, what he said, was interesting, slightly more diplomatic than the language I used. In summary, on the basis of this chapter, it seems as if Einstein knew beforehand the spatial portion of the relativistic transformations and an approximate version of the correct time coordinate. Using the spatial portion as a guide, he deduced the time coordinate from demanding that the velocity of light was invariant. It is difficult to imagine that Einstein first derived the relativistic transformations by the method described in the 1905 paper. In fact, he never used this method again. I think that's very interesting. That's a very nice and diplomatic way that it's essentially what I felt, which is he knew the answer he wanted and he assembled his calculations to fit. And the calculations were a bit bumpy. Miller says Einstein never used this method again. In fact, the next paper he had published in the subject was in 1907. And as Miller says, Einstein used a completely different analysis to develop the Lorentz equations. Basically, he developed them by starting with the relationships x squared plus y squared plus z squared equals c squared t squared, and c squared plus eta squared plus zeta squared equals c squared tau squared. Now, I'll ask you to follow me in just a little bit of algebra on that. If we're considering a clock that's on the x-axis, moving along the x-axis, then y and z are 0, and so are eta and zeta. Therefore, we have, for a clock on the x-axis, x squared equals c squared t squared, and c squared equals c squared tau squared. And obviously, following from that means that x equals ct and c equals c tau. Therefore, what I would draw from this is, although his 1907 paper had quite a different analysis from his 1905 paper, both papers, when you boil it down, the relationship from both papers ends up, for a clock on the x-axis, a moving clock on the x-axis, x equals ct and c equals c tau. He's come to the same answer by different routes. A key to the whole enterprise is the Lorentz equation for time. I understand very well why Einstein wanted, when he had completed his calculations, he wanted to present them in the same format as the Lorentz equation, because then people could see that although he had a different theory from Lorentz, he'd come to the same answer. However, we go back to that question, what is x? In Lorentz's theory, x may be an independent variable. But in Einstein's analysis, as we've shown, x is not an independent variable. It's related to t, time, by the formula x equals ct. Given that x equals ct, in Einstein's theory, you can insert CT into the Lorentz equation and simplify it. There's basically X is, in a sense, a false variable because it's not an independent variable in the equation. If you put it in its relationship, the equation simplifies to this: tau equals T times 1 minus V over C over root 1 minus V squared over C squared. And this is where the problems begin. The standard time dilation, which was already known, was tau equals T root 1 minus V squared over C squared, which is not the same as what you get if you take Einstein's theory and apply it and simplify by substituting X equals CT. You're actually got a different equation. So from Einstein's theory, so the various time dilations you can get, there's the standard time dilation equation, which was known before Einstein's paper. There's then, if the clock is at the origin of, the moving clock's at the origin of the moving system, then we have the, with X equal Vt, you have the T equals 0 equation. And if you take Einstein's theory with X equals Ct and put it into this equation, you get, I've just run around the algebra to make the implications clearer. This equation is actually the same as that. It's just expressed slightly differently. But you can then see clearly what the difference is between equation 1 and equation 3. What does this mean? Well, if you put into it finite numbers of V over C, that's ratio of speed to the speed of light, you can see this is the amount of calculated slowing you get from the standard time dilation equation. Equation 2 gives you no meaningful results. That's the one where the clock's at the origin. Equation 3, which is what you get if the clock's not at the origin, but it's on the x-axis. Now, as you can see, if V over C is 0.5, the clock slowing predicted by the corrected Einstein equation is about 3 times as much as the standard time dilation equation. And if V over C is 0.1, it's 19 times as much. So what do we know about time dilation? Well, the most widely cited experiment, quite a fancy experiment for its day, was in 1971 by Hafele and Keating, where they took a jetliner, put some atomic clocks in it, compared those atomic clocks with atomic clocks in the laboratory on the ground, then flew around the world and compared them again. It's generally held that it's quite complex to back analyze because special relativity is just about uniform motion, whereas a jetliner flying around the world undergoes acceleration. It travels on a curved path with centripetal forces, and it decelerates to land. And there's a gravitational field at work all the time too. And those all need to be taken out. But it's generally held that Hafele and Keating's results fitted quite closely the standard time dilation equation. So let's go back to the theory. If a jetliner is flying around the world, its speed is approximately 250 meters per second. Here's the predicted clock slowing by the various equations. First of all, the standard equation, 0.35 times 10 to the minus 12 seconds per second. Secondly, if we take the Einstein corrected equation, we come to 835,000 times 10 to the minus 12, which means that the Einstein corrected equation, number 3, is predicting clock slowing, which is 2.4 million times as much as the standard equation. I think we'd all agree that's outside the bounds of experimental error. If within the bounds of experimental error, the experiment and subsequent ones carried out to test this theory all agree reasonably with the standard equation, then the prediction of the corrected Einstein equation is out by a factor of 2.4 million, which is not small. Just as with the derivation of Lorentz equations, so when it comes to time dilation, I've showed you the calculation that Einstein proposed to derive time dilation in 1905. However, if you go and look at textbooks on relativity, you'll find that that way of calculating is very rarely discussed. What you're much more likely to find is a diagram that looks like that, where, again, we've got a moving coordinate system and a stationary coordinate system. This time, instead of the light flash being sent along the x-axis, it's sent along the y-axis of the moving system, so that in the moving system, it travels up and back like that. But in the relative to the stationary system, a ray of light sent in it to get to the same locations would have to travel at an angle to this point and back to there. And if you compare the two, you come up with a calculation of tau, that's time in the moving system, of that. Now that's very nice. It's a very nice, simple and easy to understand explanation. And also it gives exactly, the answer it gives is exactly the same as the standard time dilation equation. So far, so good. The problem is the fact that that thought experiment exists doesn't mean that the other ones have vanished. The other ones I showed you earlier are still there. So if you only consider someone who only considers this one, experiment 3, and ignores 1 and 2, that's bad mathematics and it's bad physics. What you get out of this is that in Einstein's analysis, the calculated time dilation depends on the position of the moving clock relative to the origins of the coordinate systems at the start of the experiment. If the clock is at the origin of the moving system at the start of the experiment, then you get this meaningless result. But that's the result. That's all you get from Einstein's equations. If the clock is not at the origin of the moving system, but is actually offset along the x-axis, then you get this equation for time dilation. And if the clock is not offset on the x-axis of the moving system, but instead it's offset on the y-axis, you get this equation. So we've got 3 possible answers depending on what the initial position of the moving clock is. And it would depend on what problem you're trying to solve. But usually we're discussing a situation where a moving clock moves directly away from the observer. I would say to you, if that's the problem you're trying to solve, then it's equation 1 or equation 2, which is relevant. Equation 3, where the clock is offset off to the side, it's not moving directly away from the stationary observer. So equation 3 is not the relevant equation. It's equation 1 or 2. And that's what we could turn time, the sharing off. Screen sharing can go off now. Can you close this? That's good. And then I'll tell you just up on screen. That's what I've worked out. If somebody can show I've made a mistake, then to be honest, I shall be delighted to have this explained, because it will say, if I've got it wrong and Einstein had it right all along, then we don't need to talk about the matter further, and that will save me a lot of time and trouble. If, however, there is something on what I've worked out, then there are some questions that need thinking about. First of all, people talk a lot about Einstein's 1905 paper, but what is its actual scientific standing? On one hand, as I mentioned earlier, according to the late and great Professor Stephen Hawking, Einstein's 1905 is still the best explanation of special relativity that there is. Yet I've also seen the recommended reading list for the Sussex University course on relativity theory. And interestingly, there's a recommended reading list at the end of the course notes, which doesn't include Einstein's 1905 paper at all. Which of them is right? Then there's the controversy about why did Einstein never receive a Nobel Prize for his 1905 paper on special relativity? Was that gross unfairness by the committee? Or was it a wise judgment? Were they making a wise judgment about a paper which was ambitious in its objectives, but actually flawed and not all correct? Moving forward to look where we go from here, if Einstein's calculation of time dilation is wrong from his theory, and there's something wrong with his theory, is it possible to revise his 1905 paper to correct the errors and amend the analysis accordingly? Or are the errors too serious to be corrected out? Basically, the question comes, can Einstein's 1905, is it possible to correct and knock Einstein's 1905 paper into shape? Or is that not possible, and we should regard it as something that isn't a paper that is now only of historical interest and is not suitable for modern scientific use? And if that's the case, it needs to be abandoned in favor of a different theory by either Einstein or some other author, if Einstein's 1905 explanation and theory falls by the wayside. Over to you. That's what I've got to say, and so I'll pass over to you for discussion.
Well, thank you very much. And my apologies for any slight delay in responding to your requests, Alasdair, for putting up the slides or for ending the session. There seems to be some problem at my end, I think I've determined it. So I hope it's not caused inconvenience to anybody else. But, well, I'm delighted that you have offered to come back after your extensive paper concentrating on the question of time dilation. I know your earlier paper gave rise to a lot of discussion and argumentation, even in some sense, and I think that's not a bad sign, actually. But you have indicated to us something which is very well taken, and I know you've been talking about this in the University of Oxford just in the last few days.
It wasn't Oxford. It was in Oxford.
Hearing maybe what the
it wasn't at the university. It was in Oxford.
It was in Oxford,
but not at the university.
Okay, because that was part of my problem. I know that some of the participants in our CNPS sessions talk, the cancellation or the boycotting or the ostracization of people who question some of these fundamental physics questions. And I was under a misapprehension that perhaps the university had hosted your meeting. You just haven't been in the town of Oxford there. But okay, yes. That's fine. It's a fascinating subject for my part. And I'd like to hear what people say. We'll have a look at the question. Unfortunately, I think there might have been a problem with the ordinary Facebook and YouTube participation. We don't seem to have many comments there coming in, but we do have a number of people from the green room. Cerna has made a number of comments there. But and by the way, I just might mention, if I'm in the general comments, which may not always have been taken, but our previous speaker, Sankar Hajra, who gave us a talk on the collapse of SR and GR, he questions, but he undertook to provide written responses to any specific questions. Now, we had questions from Robert K. I don't know if these gentlemen are here today. Robert K. Kev Con, who's actually in Ireland as well, who used the format Entrained Ether Ideas. Now, we also had comments from Professor Halem Boutenyeb. Now, I Halem, but I didn't have the email addresses of the other people. So if they care to provide me with the email addresses, I can also provide the written responses and you see, you raised a very fundamental point, which I think is worth our while deliberating on in the CNPS, that Einstein's papers can be read in many respects as endeavoring to formalize something which was already conceived of. You've expressed that quite cogently in regard to the SR and the Lorentz transformations, which had been worked out beforehand, and perhaps the work of Larmor on time dilation. And the same, incidentally, could be said and would be said by people like me, for example, in regard to certainly the aspects of GR, where he had certain quantities of secular mercurial precession and bending of light rays and so on that he wanted to get to, and he formulated theories which led to those results. And by the way, in your very interesting derivation, Alasdair, I just again was brought back to the thinking along the lines that C plus or minus V is really a no. It's verboten, and there's a constant C, and yet what's coming out of the wash is things like X dash over C minus V equals T. It seems to be a contradiction in terms. Before, by the way, handing it over just the questions, I might just say, maybe I misunderstood something, but there's a bit of confusion in how the time dilation equations work out, and I think it's compounded by the fact that gamma, using the new notation, not the Einstein notation, which you've used, Alasdair, is the reciprocal of 1 squared. But I think normally in the physics textbooks you get things like for length contraction, forgetting about gamma or beta in Einstein's terms, might get something like L dash equals L naught into the square root of 1 minus V squared over C squared, and then you get T dash equals T naught over the square root of 1 minus V squared over C squared. And yet I think you were showing in your T dash equals T multiplied by 1 minus V squared over C squared. I seem to be coming out of Einstein's position. So I wasn't a bit clear on that. You might want to comment on any of those points before we get to the questions, if I've been clear enough, Alasdair.
Yes, that last one is very simple. I agree with you that his beta being a reciprocal causes all kinds of mind chaos when you try to just think about things. It makes it unnecessarily complicated. But if you take the Lorentz equation for time as he presented it, if you plug x equals vt into it, then if you run around all the algebra, you end up with tau equals t square root 1 minus v squared over c squared. The root 1 minus v squared over c squared has reappeared on the top, but it's basically washed out in the algebra when you work it through. You start with the equation. It's the root 1 minus v squared over c squared is on the bottom, and various terms are on the top. And then you can multiply top and bottom by a term or divide them by a term.
I'm having some
and you end up
difficulties,
coming out with
unfortunately,
the equation.
with the internet.
Basically, it comes out. It comes out of the. It's a bit of mathematical simplification.
Picture goes on and off, and you see. But I do see that Nick Percival. I see your hand there, so I'll bring you in shortly, Nick. Don't worry about that. Thank you. I think I asked you all. I normally don't have these problems, but I'm having problems now.
Is there anything more you want from me at this point?
No. Thanks very much. I think we might go to the fuller discussion. Unfortunately, I don't think I heard everything you said because the thing was breaking up, and your audio, your video rather, went off as well. But it's evidently something at my end, Alasdair. I'm sorry about that, and there's very little we could do about it. Provided everybody else, I think I probably have something from Roger Anderton here, who's the sound is all right from him. It came so perhaps we'll just see if there are any general comments, and then we'll have a fuller discussion. Comments. Let me see now. Okay. Yeah, there are a couple here. Let me see now. There are people like Salmon Fish and Serna, raising a lot of very interesting questions, but they're really, dare I say, have the time to go into them today. So you'll forgive me if I do skip over most of those comments. Now, Robert K. And by the way, as you're here, Robert K. If you send me your email address that were posed to Sankar Hajra's paper, I couldn't. He provided them to me, but I couldn't forward them to you because I didn't have your email. So anyway, I just see a question from you directly to Alasdair. So let's put it up, Robert. Okay. Things are really very slow. Alasdair, in Einstein's equations, the y-axis is equal to all equals y dash. You have something different. A question. I'm not sure if I understand that. Do you follow that, Alasdair? The question.
I understand the question, and the answer is
Robert,
no.
Maybe you could put in.
Well, I can explain it clearly, I think, because I put the diagrams up in the paper. No, I don't.
You don't have something different too.
No, I don't have something different. Yes, I'm aware. And if I just
basically the other coordinates. Okay, so if that doesn't answer your question, Robert, come back, please. And
I thought I'd explain that clearly I tried to explain it with the diagram near the end, where there were the diagonal light paths for a clock that's positioned off to the side, and comparing the results of that with a clock that's on the x-axis and showing that they're different.
Yeah, this is the Pythagorean type thing.
Yes.
Well, I have things from John Chappell, Natural Philosophy Society, which basically means it's coming in via the admin. So that I'm admin, but So I think these are probably from Roger Anderson. Anyway, if necessary, he can come in. He's saying x plus or minus CT is the light cone. X does not always equal that. It is only for light that it equals that. I'm not sure if that's a question or a truism, or even something to contradict. Maybe he's saying, is it only? I'm not sure. And here's another one here. Maybe I'll put that up, Alasdair, to give me just. We'll get them out. What he says is, you see, I've tried to put it up, but it's taking its time to do that. I think maybe put in the same question twice. X plus minus CT is the light cone. X does not always equalize. Yeah, okay. Unless you want to say anything, Alasdair, we'll pass on. Or unless Roger wants to come in later when we get to the green room.
Right.
Okay.
Way better.
Yes? You're leaving it for the moment. I think Roger is in the green room. If he wants to come in, he can talk about it. But I have another Alasdair K. Maybe it's...
Yep. Do you want an answer to this one?
I'm not getting everything you say. I apologize.
I've got Robert K's
question. It may appear that I'm not responding properly. Yeah, okay. Robert K. In SR, the proper time t dash is on the y-axis. He's trying to explain the relative time t is on the x-axis and the diagonal. Then, well, that's a bit. Then t equals t dash over the square root of 1 minus v squared over z squared. What say you, Alasdair? Whereas I was asking about the other way around. That
that's talking.
I was saying actually that t is equal to t dash multiplied by the square root of 1 minus v.
That goes back to the diagram, the last diagram I put up on the presentation, which has the diagonal light paths on the y-axis of the moving system light path. And quite correctly, in Einstein's theory, if you look at that scenario, which is a scenario where the moving clock is offset from the x-axis, it's on the moving y-axis, then you get the standard time dilation equation. My point is, yes, that's true, but in Einstein's theory, if you look at a moving clock that's on the x-axis, which is actually the example that Einstein himself considered, you get a different formula. So the equation depends on the position of the moving clock relative to the x-axis. And if you position it on the x-axis, like Einstein did, you get a different equation. That's not to prove one's right and one's wrong. It proves that if you put the clock in a different place, you get a different answer. And choosing the answer that suits and ignoring the answers that don't suit, as I said in my book, is bad maths and bad science.
Okay. Questions or a couple of comments. I think maybe we can deal with one mainly, because I'm not sure if we've heard from Josef Radomansky before. He's basically saying, this is his first comment, the Lorentz factor is fine because without it, the wave equation wouldn't be invariant. This implies a constant of light. Well, this isn't totally germane to the errors that you've pointed out. I would say it's another question as to whether, he's basically saying that, I suppose, SR is correct because it does other things. So I'm not, and the other couple I think we can deal with under the same heading. If you want to say anything to it,
yes,
but it's not germane to the point you were raising, really. I might say
no, but in a way,
he's just saying that it gives you the right results. So
yes, And maybe it brings out an important point in it all. There are two separate questions. One is, are the Lorentz equations and the standard equations that physicists use, are those correct or not? And the second question is Einstein's explanation for those equations correct? And those are two separate questions. And one I have addressed. And the reason why they're separate is because Lorentz derived those equations from a different theory from Einstein's one. So you have two possible explanations for one set of equations. And what I've looked at today is Einstein's explanation for those equations valid? And as I say, I think it looks bad. That doesn't tell you whether those equations are right or wrong. It just tells you there are problems with Einstein's explanation for them.
Yeah, because only the fundamentals of Einstein's theory, then, rather than just a question. I think with regard to the points you raised about the Nobel Prize, and interestingly, my own probably worthless comment would be that I would doubt whether the Nobel Committee would have been as au fait as you might have suggested in discriminating. This was worth awarding the 1905 paper and so on was worth awarding a Nobel Prize too. But anyway, I have some comments here which unfortunately are just going on and off with me because of my poor internet connection today. Let's see, can I bring this one up? I don't know if it's it's not coming up. It's just very slow. I'm sorry. I may have to leave. Luckily, you left us plenty of time for discussion, so I think we mightn't be so strapped for time as we normally are. Time will catch up on us soon enough. I may have to. Right. I don't know if you lost me actually, Alasdair, but maybe I can just read out some of these comments. He's saying, I think it's Roger Anderson, but it's under the admin. Nobel Prize is awarded for work related to relativity. 1993, Russell and Hulse and Joseph Taylor for discovering a binary pulsar whose orbit decayed exactly as predicted by gravitational wave emission in general. Sol Mutter, Brian Schmidt, Adam Rees for discovering the accelerating expansion of the universe, which relies on general relativity's cosmological framework. Dark matter 27 Rayner. I don't know what point he's making. He's just giving a lot of information there. Then he goes on. I think he said it again. General relativity. Yeah. Okay. Yeah. Okay. That's just okay. Okay. Okay.
Right. Hello.
Okay. There are people asking
Hello.
about other things which are not related. Is that
Hello.
Roger? Roger,
Hi.
could you hold on a moment, because what we'll do is we'll come back to your comments in a moment.
Okay.
So would you mind if I put you down for the moment, and we'll bring you back to explain that. What I merely wanted to do, Alasdair, is I wanted to make sure that we'd gotten through the comments before inviting people to come in on the green room. And I think Roger's comments, I would bring him up first because he did ask for the floor. That's assuming he still wants it. So, Nick, you are up now. And if you'd like to present
Hello.
Or make any comments, please do
Alasdair.
so.
Can you hear me? Yes, good.
Loud and clear.
But just by the way, I could hear Alasdair perfectly, but Ian was fading in and out, and I think there was a great delay.
I think it was only I that had the problem.
Yes, yeah, and you were talking over Alasdair because I think the delay was such that you were hearing Alasdair a lot later than we were hearing Alasdair. Anyways, Alasdair, I thought that was a great
I'm so sorry.
And a lot of really good points. I've been looking at this issue for about 60 years now, but I've been looking at it from a different perspective. I think sometimes it's very difficult to follow math manipulation step by step. I tend to look at it from the physics that's involved. So I'll try and interpret the physics of what you were saying. First of all, of course, Lorentz's original transformations versus the special relativity transformations, called Lorentz transformations, look identical physically, but they're not the same. They are at opposite ends of the spectrum in terms of their physical meaning. And I think that people looking at the equations and saying they're mathematically identical brings in a lot of confusion to some people. Some people even claim that the original Lorentz transformation equation to predict that the speed of light is physically c in all inertial frames. In Lorentz theory, there is one physical model of the applications that we are talking about, length contraction and time dilation. And that single preferred frame is the ether rest frame. And just by the way, the data from GPS seems to confirm that view, that Lorentz original transformation equations were correct, and that the so-called ether rest frame, at least in the vicinity of the Earth, is the ECI frame, the Earth-centered inertial frame. And that if GPS tried to use relative velocities with respect to any other inertial frame, they would be sending people off into people's houses and whatnot. And I think the other important point is that there's nothing wrong with the relativity principle, but there is something very wrong with how Einstein interpreted that. For some reason, he thought that for light and measuring the speed of light, that you could forget about the ether and think that the physics equations have to be exactly the same. In other words, you can't talk about the speed of light with respect to its medium. And that was the problem. If you applied that same rationale to say, hey, in looking at sound waves, we can't talk about the sound with respect to the air or whatever medium it's traveling. And if you use that same incorrect interpretation of the relativity principle, you'd end up with all sorts of nonsense and zero physics, which would only be correct if you happen to be at rest in the medium for sound when you're looking at the physics of sound waves. And so I found that your math presentation was showing where they went wrong in the physics in terms of how I'm explaining it. So one point about the original Lorentz theory is that there is one physics theory, and you have to use the ether rest frame as the single preferred frame. So what Einstein did, per what I just talked about, was make the mistake of saying that in terms of these two phenomena, length contraction and time dilation, that all inertial frames are simultaneously the single preferred frame. In other words, an infinite amount of contradictions. And I think you showed where that went wrong with your math. Thank you very much. Appreciate that. So it's good to have both, I think, the detailed math, which you did really well in your first presentation and again here. And I'm just trying to add on top of that the conceptual physics implications of that, which is probably easier to grasp on the fly in a presentation like this. So again, thank you very much. And that's what I have to say.
There's expansion to the time dilation, concentrating on that was useful indeed. I agree.
Oh, good. One other point.
If that's it, the basic point, Nick, any response to that? Okay, go ahead.
One other thing, I see that James Keane made the point about is there any evidence for time dilation? And some people might say, oh, yes, GPS has proved that. But no, GPS shows that there is Lorentzian clock retardation, at least for clocks that are driven by atomic processes. But empirically, it's been shown that there is no time dilation because different processes are affected differently by velocity and gravitational potential. If time dilation were true, as Dingle pointed out, then all clocks and all other processes would have to slow down by the same rate. And we know from empirical evidence that that's not true. So time dilation has been empirically disproved, and what we have is atomic clock retardation. Thank you.
Any comments on that contribution by Nick, Alasdair?
Two brief comments, and I'll include Jim Keen's one in it. What Nick says, I find very clear, and I come from a background that says if it's good science, then there's the maths and there's the physical reality, and each of them has got to make sense in its own right, and then they've got to make good sense when you match them up to one another. And if you've got the right answer, there shouldn't be a problem in fitting them together, which I think is what Nick's saying. Mm-hmm. On regard to Jim's one, I'm not arguing whether time dilation exists or not. I'm simply looking at how Einstein, the theory that Einstein presented for it and how he calculated it. And Jim says that draws attention that distance and time are related and not independent variables. And yes, I agree with you on that. I'm aware of it. And yes, I agree with you. And maybe I didn't put it over clearly enough, but that was actually one of the key points I was trying to put across, that you take the Lorentz equation, which has an x in it, but in Einstein's theory, that x is a function of t. It's not an independent variable. So it's actually a much simpler equation dressed up as the Lorentz equation. And if you can take the x out of it, and the point then is that you get a different time dilation equation. And as Jim asks, is there evidence that time dilation exists? I would say, I don't know, but if you take my calculation of time dilation for a jetliner flying around the world, if it's debatable whether there's any evidence for time dilation, then Einstein's theory predicts 2.4 million times more time dilation than the standard equation. And I would say to you, whatever evidence there is for the standard equation, there is no evidence at all to support the proposition that time dilation is 2.4 million times as much as the standard equation, which is what you would have to come to if you followed Einstein's maths and theory.
All right. Yeah, we're getting a lot of interruption, I'm afraid. But so, Nick, I might go a little further, Alasdair, in regard to this. And just ask you. I mean, you very cogently describe these errors in deriving something that perhaps he wanted to get the end result of. But I might go a bit further and ask, do you think there's any validity in the Lorentz transforms in any form, whether applied as a Lorentz in a sort of an ether theory, or whether you were asked about time dilation now because that's what you spoke about, but whether you think there is an actual length contraction in reality? But do you personally hold with there being something to the Lorentz transforms, or do you think that actually they're erroneous?
I have some thoughts, but not big enough and deep enough knowledge to answer your question.
I'm putting you a bit in a hot seat now, but just
yes,
putting a direct question.
Did
you get it, Alasdair? It's breaking up here.
Yes. Yeah. Oh, just a quick on the breakup. You may find if you've cut your video feed but keep your audio on, sometimes on Zoom calls, people have found that was a solution.
Yeah, just a second.
Is it reduced the bandwidth required? But that was just on your personal video feed. Anyway, by the by, to answer as far as I can your question, I don't have the knowledge. I've thoughts on the subject, but I don't have the knowledge to give a definitive answer. What I have looked at is, what I've focused on is not does time dilation exist, but does Einstein's explanation that he proposed in 1905 for time dilation, does that make sense? And so back to when I said there are two questions. One's the validity of the Lorentz equations, and the other is Einstein's explanation for the Lorentz equations. And my answer would be, I'll pass on the first question. Maybe they're valid. Maybe the Lorentz equations are valid. Maybe they're not. However, I think the evidence I've presented says Einstein, if they exist and are right, then Einstein's proposed explanation for them is wrong. The equations can survive without Einstein.
Well, that's certainly fair enough, because your paper has concentrated on the question of the validity or otherwise of Einstein's derivation of these, and I was asking you something which is extraneous to that. It was going a bit further.
Oh, it's a good question.
Thank you for being so open anyway in regard to that.
I have
Do you
an
want to say
answer
something else,
to your
Nick, before
question,
we move on?
Ian. The experimental evidence from GPS confirms the Lorentzian atomic clock retardation, and it disproves time dilation.
Yeah, okay. I know you believe that, Nick, and I don't. We disagree with that. So there's no point in
Ron Hatch
getting into a conversation now. I was
Ron
really asking Alasdair's opinion.
Yeah, Ron Hatch
about it. So thanks very much anyway,
confirms
Nick. Thank you.
My opinion.
Okay. Okay. Thanks very much for giving us your opinion. Is that all right? I'll bring you down now and move on. Thanks very much, Nick. Roger wanted to. I'll bring you in after this, Denny, if I may. Roger had asked to amplify, I think, some of his comments. So I'll give you an opportunity, Roger, of coming in if you wish, because it was a bit unclear. And of course, my internet problem is making matters much worse, I do confess. So if you can clarify what you're getting at, Roger, a little for Alasdair, that would help.
Yeah. Okay. Thank you. I'm sorry, but I'm having problems with my end as well.
Can you hear me? I'm asking you. Do you want to say anything?
Can you hear me?
Oh, okay.
Can you hear me?
Yeah, there's a delay with me, though. I can hear you.
Okay.
Can you hear Alasdair?
So sorry, I've had problems my end, and I wasn't able to join at the beginning of the talk. So this is, I didn't really want to come on because of that, because I've only sort of like half gathered what's been said here. But I picked up on a few things already, and Alasdair seemed to want to make a big point that Einstein didn't get a Nobel Prize for relativity. But since then, other people have done work, and that has been related to relativity, and they have got Nobel Prizes for that. So from the mainstream point of view, relativity is a well-established theory or theories. And so when I pick it up for what we're doing now is going back straight away to Einstein's 1905 paper. And I agree, it's a very badly written paper. And so it's taken physicists, mathematicians and so forth since then to try to understand what was really being said by it. And the main points that are being pointed out are it's given the Lorentz transformations, it's given the principal relativity, and it's given the idea of the constancy of the speed of light. So the core ideas of relativity were presented by Einstein in 1905. And since then, the physicists have evolved the theory, or theories, as you want to call it. So when you're attacking the original paper on it, it's sort of, well, that's not really what's there anymore as to what's going on. So it's sort of like, from my point of view, kind of like a diversion by pointing out these problems, because you've got to really deal with what's the theory now evolved into. And a couple of comments since have become really relevant to me from what Alasdair was saying. He said something, if I try to quote it properly, that it comes from a background where maths and physical reality have to make sense. And I don't think that's what the physicists are doing. That they are just looking at the mathematics, and the core maths is the Lorentz transformations and so forth. And they're saying, does that fit experiments? And they're saying, yes, it does. That fits. So the theory is correct. And of course, when you go back to Einstein, his math, it does not really make sense in 1905. And so you have to make allowances for that. And so when you're saying, oh, the equations can survive without Einstein, well, Einstein was seemingly taking the one forming the first ones for that. So you've got a problem with how physicists are dealing with relativity. And when Nick Percival was pointing out, it should be understood by Lorentz, what Lorentz says about the Lorentz transformations. Well, when I have talked to physicists, and many of them do have a Lorentz interpretation of GPS and so forth, when they're applying the mathematics, they do think of it in Lorentz terms. That does not mean that they all think in those terms. You've got a diversity of opinion upon that.
Yes. And that's what I was trying to get at.
Yeah.
Okay.
So you've got a difference in
thanks, Roger.
opinions.
Those are interesting points. And I think, if I may say so, correct me if I'm wrong, Alasdair, that Alasdair has kicked for touch a bit in regard of the derivation of the Lorentz transforms using this Einstein method. Now, whether they have some, through reinterpretation, they could, or even whether the Nobel Committee knew enough about to be able to distinguish, these are other interesting matters. But would you like to say anything else in response to Roger's points, Alasdair?
Yes. Roger says I made a big point about the Nobel Committee and the Nobel Prize. Sorry, it wasn't a big point at all. It was a small question, a small interesting question to throw out to people in passing. It's not a big point in any way at all, as it's just a question. When it comes to all the different interpretations of relativity, I know that there are many different people have many different interpretations of relativity. I mean, make no excuses for doing what I've done, which is the one that gets talked about the most and is still referred to as being great is Einstein's 1905 paper. I wanted to, in a sense, clear out the cupboard a bit there. We're told it was a great breakthrough. There was all sorts of fuss on the 100th anniversary of it 20 years ago. And just to get clear, what's the status and standing of it? Yes, it was a long time ago. Doesn't mean we shouldn't look at it and say, hang on a minute, did he get his calculations right or not? And I think in many ways, it confuses matters because students get taught, some are taught along the lines of what Stephen Hawking said, which is this is the best explanation there is of the theory. And there are others are taught different explanations. And that confusion on top of a difficult theory doesn't help anybody. So I'm sticking where I am, which is getting clear what does or doesn't stand on Einstein's paper. That needs to be established. And as I said before, that's a separate question from the question of are the Lorentz equations valid? Because they are not necessarily dependent on Einstein's theory. Einstein's theory is one possible explanation of them.
Okay, thank you. So I think what happens is students get taught relativity, and if they do actually then go back and look at Einstein's 1905 paper, they do get surprised what Einstein is actually saying in that paper, because what they're being taught seems to be quite different most of the time, in my view. So they are very surprised by that. With you quoting Hawking, Professor Hawking, I wouldn't think that he would have approached understanding special relativity from Einstein's 1905 paper. He would have gone through a standard undergraduate and then graduate courses in relativity, and so his background would have been understanding relativity from what he'd been taught by others. He would have then approached reading Einstein's special relativity paper in 1905, and he would have been then imposing his beliefs, what he'd already acquired from being taught. So he to him, it would make sense because he's making allowances for things. But if you were just approaching special relativity straight away from Einstein's 1905 paper, then it can be very confusing, because that's not what they're going to teach you at relativity courses. You first need to go on relativity courses to understand special relativity from what they're telling you now in a modern context, before you can then read Einstein's 1905 paper and make allowances for the sloppy way he's doing things. The way he's doing the mathematics is very sloppy.
Okay.
The way he's talking about things is very bad. Thank you.
Yeah. Okay. Thanks very much, Roger. So just really, may I ask? I mean, Roger was making points about what's accepted, and just to ask, Alasdair, I made a mistake about thinking you were involved with the University of Oxford. Do you mind telling us what was the aegis of the body that invited you to give this?
Oh yeah, it was the Alternative Natural Philosophy Association, ANPA, which are quite an interesting bunch of people with various interests in science.
Oh, there's an
Alternative Natural Philosophy Association.
This is in the UK, or is it international?
It's international. It's international.
Okay. Okay. Okay.
Some of its members have contact with.
Danny wanted to come in as well. We'll keep an eye on the clock here. So, okay. So, have got what? Yeah, some of its members, unfortunately, you broke up then.
Oh, some of its members are also in contact with the John Chapel Society. There is some overlap.
Okay. Okay, very well. Yeah. Right. Which is not too surprising, perhaps. Okay, we might need to look into that and perhaps see is there any liaison which is worth husbanding. Now, Denny, I've brought you up so you can make any points you wish.
Start out. Excuse me. I'd just like to start out by remarking that I've heard some very bad things about the Hafley-Keating experiment methodology. They seem to be, what I heard anyway, was that it was basically another attempt to gain prestige in the academic community by getting the right answer, no matter what the cost. I think it was Wesley who, J.P. Wesley, who made points. Yeah, but he has two books here, Scientific Physics and Light of Photon Flux, and it's not mentioned either one. It must be some of his previous books. I don't have them here. I'm in a new apartment because my old apartment, there was a water pipe breakage and I was flooded out. So I don't have most of my books here. But Hafley-Keating, you read papers where they basically admit that if they don't get the right answer according to what the physics elites say, then something bad will happen to them professionally. And Hafley-Keating seems to be just another type of that sort of thing occurring, from what I've heard. And also, I wanted to mention that made the point that Lorentz theory is superior to Einsteinian theory. But I know, Ian, you've written a paper whose title I can't ever remember. It's something about analogy, and showing that if you use the usual hydrodynamic way of looking at in electromagnetics, if you adopt the Galilean transformation point of view, which everyone thinks doesn't work for relativistic effects, you do get much better answers. And I want to mention that because a lot of people are frustrated with Lorentz theory in electromagnetics, which is not, it's understandable because, for example, Ron Hatch didn't use it. He had introduced this transformation due to celerity, and got from he was Ron Hatch was the last of the big GPS people, and he had to throw out the Lorentz transform because he wasn't getting the right answer. You see, he was an engineer and he had to get the right answer, not the right answer according to the physics. And consequently, he's never gotten any Nobel Prize or anything, despite the fact that the reason that GPS is so accurate nowadays is basically due to his work, like the 2007 paper in Physics Essays, the same paper that Alasdair same journal that Alasdair's paper was published in. This paper by Ron Hatch was published in the 2007 issue, and it starts out with the title starts out with a new theory of gravity, where he, according to GPS, which works, by both special and general relativity were incorrect, based on the wrong answers they got. Not the wrong answers in relative to the physics elites, but wrong answers according to people who are trying to build a GPS system that works and succeeded. Because as we, you even have them in all automobiles now, new automobiles that are produced. And but his theory was not in line with what the physics elites proposed. Roger has made a big point of this.
Are you familiar with Ron Hatch's work?
I read one book of Ron Hatch's, and I'm not expert in all the stuff, but I could tell this was a man that knew what he was talking about. The other one is on the Hafele and Keating experiment. I've got Al Kelly's book on relativity, where he goes into the Hafele-Keating experiment in considerable detail of what really happened, and he got access to the raw records of the measurements rather than the tidied up ones as well. It's not to what I'm looking at today, for what I've been looking at today. I can see it's very important for other things, but it's not very important for what I'm looking at today, because what I've come up with today is that if there's time dilation, clock slowing does occur for whatever reason, then a correct application of Einstein's theory says that it should be 2.4 million times as much as predicted by the standard time dilation equation. And whatever rough and readiness there may or may not have been in the Hafele and Keating experiment, I'm sure they would have noticed if the answer was out by a factor of 2.4 million.
Yes.
Okay, well, that was certainly an interesting aspect that you raised.
What is the title of that paper of yours, Ian? What is
Uh,
it? No analogy.
Yeah, I think it may be the one on electromagnetic radiation anomaly, no analogy. I think that might be what you're referring
Yes.
to.
Yes.
You know, like the conventional
That's right.
physics would say it's anomalous. Electromagnetic radiation or electromagnetic waves are anomalous compared with all other types of radiation. For example, this magic constant speed of transmission. But I say no, it's analogous. And you've given the reasons why you use the similar mathematical treatment that you would in, say, fluid dynamics or whatever. Yeah. So
It was you, Ellie, in electrodynamics, weren't you?
thanks for that, Danny. The whole question,
You were
maybe
published in
just
Galileo
before we end. I think it was in Galilean electrodynamics. Yes, Dennis. But I mean, see, this whole question is really erroneous to the errors that Alasdair has been pointing out today. But what do you do to get real results which are accurate, in real life, and helps you to navigate, put you into a lake or something? Well, I think most of the comments here, most of the people here would say that time dilation is not correct. I talk about clock retardation, but then you can go further and say, well, are the Lorentz transformations, to be blunt, my opinion is actually irrelevant for today's discussion. But I think the Lorentz, there's no reality to them at all. They're a trick. And I think I always prefer to use physical explanations for things rather than magic transformations. I'd always prefer to that, certainly in the first instance. But it's a whole other subject as to what results from Alasdair's having pointed out these errors. And I think maybe Jim Keane, I don't know if he wants to come in, but he's saying, Alasdair tried to deal with some of the points Jim raised, but he's saying, so what is the correct theory? So perhaps, Danny, if that's all, I'll maybe bring you down and just ask Jim. He might be our last speaker in the green room. But is anything else you want to raise before we leave the point? You referred to Wesley's work. It was breaking up.
What year was that article published on no analogy paper? What year was that published?
I might have to give you that offline. I think it might be about 5 years ago, but I'll let you know. I'll send you the date of that if you wish, whether it was 2019 or 2020 or 2021. It'll be in the last few years. Okay, so thanks very much.
Yes, it's
for raising all that, Danny. So I don't have immediate control here. There's always a delay, but Jim, would you mind if I imposed upon you, as I sometimes do? You've put a number of questions in there, or a number of points, and I don't know if you want to expand on them. Like, for example, you say, what is the correct theory? So as a result of what Alasdair has been saying, what should flow from that? I can't hear you.
Question I was asking that, if we have these problems with the Einstein approach, what is the correct theory? Does Alasdair think that there's some relevance of the Lorentz transform to physics, for example?
The question what the correct theory is a bit above my pay grade. I'm interested in the subject, but I wouldn't claim the knowledge to know it. All I've done is look at Einstein's one, and I know I can spot him. I'm fairly good at spotting mistakes or when somebody's got things wrong. That if we knock his theory explanation out of the way, that opens up the field to other people with better ideas. But I'm interested to see them set out, but I don't claim to have that knowledge.
Fair enough. Okay. Well, it seems like the question is why this is even a topic in a forum which is supposed to be about science. Because here, for example, like, do you think, for example, there's an arrow of space? We have an arrow of time, and we're going to mix time with space. So does X, Y, and Z have an arrow too? You can only go one direction there?
Jim, you come up with some really good questions, and the bloke you're asking them is a bit too dumb to answer them. I'm sorry. They're really good questions, but I can say I don't know for quite a few times if that would cover it.
Yeah, you know what? I'm going to applaud. In many weeks of these sessions, one seldom hears a person, an intelligent person, such as Dr. Beal, um, say, "I don't know the answer to that." And I think we ought to get into the habit of following his example here. It's like of admitting we just simply don't have an answer, rather than making up some kind of coyote and roadrunner cartoon version of science that we have now. Like my big question about this, not to give a big speech here, but just real quickly, is that you lose time as an independent variable. From everything I've read about the Lorentz transform, the whole point is the invariance of the laws of physics. But if you've taken time and used that as a position coordinate in your system state, then you don't have any laws of physics which are time dependent. You've already used the time variable. So there are no laws of physics to be invariant across a Lorentz transform. And so I'm wondering why we're even talking about a Lorentz transform in the first place. It's just not science. End of speech. And I want to thank you, Alasdair. You seem to be a wonderful guy and a very bright mind, and I enjoyed your talk, sir. Thank you.
You're very kind. Thank you.
Thank you very much. Okay, well, thank you very much, Jim. So I'm just answering a question there. I'll bring you down there. Some of those points which Jim raised were actually the points which were in my head as well. So I was going, okay. Okay. Well, I think it's time now to consider wrapping up. We have a few more minutes left, and I always like to give time to the speaker to have some minutes of further uninterrupted stage time to summarize what he did today, perhaps summarize what he didn't. He didn't want to answer the questions about why the universe exists and so on, and perhaps supplement some of the material that he has already given, many of which are quite deep. And one once he's done that, I'll come back and perhaps officially close the meeting to myself, Dan, which will mean that you will have the entire floor to yourself. And I'm sorry if there's a delay in my operating these things because everything is so slow.
Thanks very much for that, Ian. I don't have much more to say. I've found this afternoon very useful. What I was particularly looking for from the afternoon was to get people to engage with the questions that I've raised. Whether to tell me I'm wrong or right is less important. The important thing is to engage with the questions, because it's amazing how some of the big stuff in physics people don't really talk about. They talk about special relativity as if it's done business. There's no more to discuss in it. And then you go and you read Einstein's paper and you say, what? Really? And so what I'm keen to do is to actually clean things up, see if we can clean things up a bit, sort the wheat from the chaff, as the saying goes. If there are things, if Einstein's paper is wrong, well, let's clear it out the way. And it doesn't answer all the big questions that remain, like Jim said, but it clears the decks a bit. So I would say thank you to all of you for actually engaging with the questions, asking good questions, making me think about it a bit more. And I hope maybe yourselves thinking about it a bit more. I've enjoyed it. So that's really all I've got to say. And I hope you found it useful. And I wish you well, everybody.
Hello, you're on stage now, Ian.
Okay. I was cut out of the session, and I would have thought that most undesirable to break it up then. Now, did I see Nick wanting the floor again? Do you want the floor again, Nick? Okay.
Artie, I wanted to correct a couple things.
I'm sorry for the bad reception.
Okay. Both Dennis and
Yes, Nick. What
James
did you want to say?
were using just said Lorentz transformation as if there were one. I have to. This is one of my hot buttons. There are two totally different versions of the Lorentz transformations. Lorentz's, which was based on a single preferred frame and absolute velocity with respect to that single preferred frame regarding clock retardation and length contraction. And GPS confirmed time dilation. I'm sure confirm clock retardation with respect to absolute velocity with respect to a single preferred frame. We don't know if it's an ether frame or a gravitational frame, but it's the Earth-centered inertial frame. If you try to apply Einstein's version of the Lorentz transformation and use an inertial frame other than the ECI frame, then you get wrong answers. So basically, the empirical data, according to Ron Hatch,
Right, Nick.
and
I'm
many others.
sorry, we've quite run out of time. Yeah.
Okay.
Okay. We really have to close now, Nick.
Okay.
Thank you very much. Could I suggest that you might do this offline, maybe make those points by email? I'm so sorry to have to cut you off, but we've quite run out of time, and I just have to stop the thing now. So thank you very much about the difference between the two systems and Lorentz's early work. It's very important to consider that. Thank you, Nick. Thank you. So very, very quickly now, at least if you look at the recording, you're going to find that I'm behaving very erratically. I'm interrupting people and taking a long time, but at least you'll hear the speaker. I couldn't hear the speaker. He was on and off. So I'm going to have to listen to the recording now to get a proper take on what actually happened today. So you will forgive me for that quirk. The system is not normally so bad at my end. But on behalf of the CNPS, I'd like to thank Alasdair very much, obviously for coming in the first place to give us the talk on his discoveries with regard to the 1905 paper, which in many respects is considered sacrosanct. And then for going into further details after his very impressive paper. I mean, I've had a look at I've read his paper in Physics Essays, and I'd ask many of you to do that as well. It's well worth it. He's a very clear expositor, actually, and he quotes maybe people like Hawking to support his contention, but he's doing it as a first principle. Always go to the original source. Don't look at second-hand or third-hand points. I think it was Dr. Johnson who was meant to have said when some youngster gave some information, he said, "You will find it a very good practice, sir, always to verify your references." So, that's ANPF. So Alasdair has gone into great detail in explaining this matter to us, and he's gone to the actual equations using even the same terminology that Einstein did. So there's no possibility of his obfuscating the matter. He's been very, very clear, and actually he's been very noteworthy in not spoofing on if he's asked other questions which are ancillary, or what are you going to do now to modify existing ideas, or how we solve this. He says, "I don't know." And as Socrates said, it's a superior position to be in, to say that I don't know rather than that I know it all. And unfortunately, too many people in the modern world, and I don't exclude scientists, say I know it all. So it's a superior position to say I don't know. It's something we can do further. So I must close the meeting now, and wish you all, wherever you are, a very good day. I hope you found it useful to experience what Alasdair had to say today. I'd like to thank him all very much. Thank you all for your questions, for your contributions, particularly people in the green room who are very active today, and they've all made very, very good points. And thank you, Alasdair. Let's keep in touch. I probably said this the last time, and it did bear fruit. It might have taken some time to bring you back, but I hope we'll hear more of you, and we might have an opportunity to hear from you again in the light of your developing researches in the not too distant future. So I'm going to close the meeting now and wish all our participants a very good day.